Hello everyone, thank you for joining this talk. My name is Ricardo, I'm a software engineer at Collabora, and today I'm going to talk about fuzzing the Linux kernel and how to use Syzkaller to fuzz a Linux driver. So let's get started. So before we begin, let me give you a brief overview of what the talk will be about in more detail. First of all, I'm going to start by giving a short introduction to fuzzing in general, what it is and how it works, and why it is a valuable tool in the for Linux kernel development. Then I'll introduce Syzkaller for those of you who aren't familiar with it already. I'll show you how it works, what are its key features, and how to configure it. And once we are familiar with Syzkaller, I'm going to show you how to use it to target a specific part of the kernel. In this case, a particular driver in a dedicated hardware board as a test machine. And finally, I'm going to show you how to get results from Syzkaller and how to use them. Software testing is a very large area. And over time, it's becoming even more complex and developed, which makes sense because, as you may know, most of the time in software development is spent in maintenance and debugging. And testing is a way to help us reduce both the number of bugs and the time we spend looking for them and trying to fix them. Now, there are many approaches to software testing and different techniques with different goals. In this talk, I'm mostly interested in using testing as a way to find bugs. In this regard, there are two main methods, or at least two of the most well-known and most used, which are unit testing and, on the other hand, fuzzing. Most people is already familiar with unit testing as part of the software development process. Unit tests try to check that a certain piece of code behaves as documented. So developers and test writers manually write tests to make use of a function interface and try to cover the documented functionality, including corner cases and edge cases in function input. And if done correctly, over time, this test will help catch bugs when they are introduced. For example, when a certain feature no longer works as documented, or when a code error is introduced in the path covered by the test. Fuzzing, on the other hand, is a more automated process and doesn't require you to write any kind of test manually. What a fuzzer does is instead to generate random or semi-random sequences of instructions as programs, including also randomized data inputs to try to trigger certain bugs that went unnoticed in the first place. So the idea is to produce both data inputs and runtime flows that may be similar to the one found in a real use case. And beyond that, that is to also create patterns that trigger bugs in code parts that aren't normally executed in a normal use case, but they are there and had to be found. In summary, a fuzzer will try to come up with non-conventional data inputs and interactions that are hard to get in a manually written test. When fuzzing the Linux kernel, the test surface is the system call API, which is the part that is accessible from user space. So a kernel fuzzer will generate sequences of system calls with semi-random or data inputs to try to crash the kernel, and then it tries to be aware of that when that happens. Now, there are many types of fuzzers, and not all of them use the same strategies and the same techniques, but in order to make fuzzing effective in a target as big and complex as the Linux kernel, there are at least some number of key features that we want in order to make the fuzzing process more effective. Because otherwise we would be relying only in pure luck. So in order to make the fuzzing process more directed and more informed, we want at least this series of features, which is first of all the ability to check code coverage during the test, so that the fuzzer can do a directed search instead of a random one. We also want some way of getting information about the source code, so that the fuzzer can generate test programs more efficiently. It's also good to have the capacity to generate data input and code sequences in a random but smart way, because we want the two things here. We don't want something that looks like a manually written test, but we don't want a completely random test either. And of course, having a good report generation, it's also important, because when the fuzzer finds a bug, it's good to know that there's a bug, but we would also like to have some information about how to reproduce it. Now, of all the kernel fuzzers that are available, Syzkaller is one of the most recent efforts, and it's probably the most successful today. So we're going to see how it works and how to use it to discover bugs in kernel code. Syzkaller appeared in 2016. It was written by Dmitry Vyukov, and it has become one of the most important tools to make the kernel more robust and more secure. It's a coverage-guided fuzzer. We're going to see what that means. And it makes use of many kernel debugging features to make the fuzzing process more efficient. Now, what does coverage-guided mean? Well, Syzkaller, as any other fuzzer, will generate sequences of instructions as test programs. In this case, the instructions will be mostly system calls. But this generation process is not completely random. Instead, what it does is to keep track of the amount of kernel code that ran as a result of running each of these generated programs, and use that information to guide the code generation process. The idea is to cover as much kernel code as possible. So when Syzkaller mutates its test corpus, we're going to see in a while how that works. Code coverage is one of the most important aspects of it. This means that a program that covers new kernel code has a greater mutation potential. Now, as we saw, in order to improve the fuzzing process, Syzkaller uses a few kernel debugging features. The most important one is kcov. Kcov is something you can enable when you are compiling the kernel, when you are building it, and is key to Syzkaller. What it does when it's enabled is to make the compiler introduce instrumentation code all over the kernel code, so that the kernel can keep track of the code coverage and share this information with user space. Then Syzkaller will retrieve this information and check the code coverage when it runs one of its test programs to see how effective it was. Another feature used by Syzkaller are kernel sanitizers, such as KSAN, KTSAN, KCSAN, etc., when available, of course. These sanitizers offer runtime detection of certain error conditions, such as out-of-bounds memory access, or null pointer dereference, or data races. And they are also based in compile time instrumentation. And the combination of an automated tool such as a fuzzer that generates programs and runs them automatically with these sanitizers is already a very good tool to detect some bugs, some very simple bugs which are not tied to the application logic, but are simply programming errors such as null pointer dereference. And this combination is able to discover new bugs automatically in a very simple way without barely any human interaction at all. Additionally, Syzkaller can also use the kernel fault injectors such as failslab or fault-futex to make the kernel introduce control faults during a test. And what Syzkaller does is to selectively enable these fault injectors so that it covers even more code that normally would be executed only when one of these faults happen naturally. So normally there are very little chances of getting to this deep code, checking error conditions and such. And fault injectors made code coverage of these blocks much easier. Now we're going to take a look at the architecture of Syzkaller in a global way. The slide shows a diagram of the architecture, and you can see it's divided in 3 agents, which are sysmanager. Sysmanager runs in the host, and it starts and monitor and restarts the targets, which may be virtual machines instances, or in this case, a Linux system running on a dedicated board. So it starts the sysfuzzer processes in the targets and is responsible for the persistent storage of both crash reports and the test corpus. Then a sysfuzzer runs inside the test target, which is a completely separate environment from the host where sysmanager runs. It keeps a communication channel between two sysmanagers, so even though they run in separate environments, they communicate between each other. And sysfuzzer guides the fuzzing process and sends whatever input it created that trigger new code, that cover new code, it sends that back to sysmanager for storage. And finally, Sys executor, which also runs in the target machine, whatever it is. It processes the test program created by Sys executor. So it accepts the program, runs it, and sends the results back to sysfuzzer. The programs here are simply C++ programs generated by sysfuzzer, and they are statically built and standalone programs. Syzkaller uses a user-defined high-level description of the available system calls described in a domain-specific language called Syslang. These definitions, this information, lets Syzkaller generate more thoughtful code using reasonable parameters and usage patterns instead of simply generating random sequences. So for example, the open system call. For this system call, it makes sense to use a path name parameter that looks like our actual file path. Because if we simply relied on inputting random strings for this parameter, it could take forever for the generator to create a string that by pure luck looks like a file path. So most of the time, the system call will simply bail out when checking this parameter, and we never get to reach the interesting parts of the code of the system call. So here's an example of definitions in Syslang of open, close, and read. You can see that the file parameter doesn't take a string as an input. Instead, it takes a file name data type, which is defined as a string with path lag formatting, a string that looks like a correct file path. And also the system call flags are defined for the same reason, to avoid simply using random integers here, which would cause the error, well, the parameter validation code in the system calls to bail out immediately. However, the fuzzer will still use some random numbers in these kind of parameters. Especially, it will try to input some carefully crafted integers to test the edge cases for these kind of parameters, because it can trigger some bugs. It's interesting to do so, but most of the time it will find more interesting results by using the information provided by the user here. Now, assuming that we have a test setup that is ready to be used by Syzkaller, for example, a virtual machine image. By the way, this is pretty well documented in the Syzkaller documentation. Now, to start a test, we have to create a configuration file that describes the target environment and the system calls that we want to enable or disable for this test. Here's an example in the slide. And once everything is in place, we can start Syzkaller by running sysmanager in the host and pointing it to the configuration file that we just wrote. Once Syzkaller starts running, it will take control of the target machine, and it will boot it, will configure it, and run sysfuzzer in it, keeping a communication channel between sysmanager and sysfuzzer. After that, it will start growing the test corpus, generating test programs and running them, and keeping track of the amount of kernel code covered, as well as the possible crashes when they appear. The evolution of the test corpus is influenced by internal heuristics and also by the priority given to each of the elements that's already in the corpus. So initially, the test corpus may contain only primitive instructions, very simple system calls, and over time, as the test programs go uncovering new kernel code, the test corpus is mutated, taking these programs as a basis for new ones. Finally, I should also mention that Syzkaller starts a local web server with a web GUI that's shown in the slide, where you can check the current test corpus, the system calls that are enabled, the current code coverage, and also the number of crashes and their reports. So now that we have a general idea about Syzkaller, well, we're going to see how to use it for a specific use case, which is fuzzing a driver in a dedicated hardware board. Now, there aren't many requirements on the type of machine that we can use, as long as it can run Linux and that it has a network link with the host, because the host will open an SSH session to the target machine. We can use whatever we want. So I'm going to use Rock Pi 4 board because the driver that I want to fuzz, which is the Hantro Video for Linux 2 driver, runs on that hardware. So First of all, we have to prepare the runtime environment for Syzkaller, because obviously Syzkaller expects the target machine to behave in a certain way, known way for it. So the Syzkaller distribution already includes some tools to make this process automatic and to generate file system images for different types of targets. The create image script in the tools directory can be used to create a generic file system image that is suitable for Syzkaller to use. And also, of course, the kernel should be also generated with at least a set of debug options enabled, which is, this is all well documented in the Syzkaller documentation. And you can see that at least it enables and configures kcoff and one of the sanitizers here, KASAN. As well as, you can enable any other sanitizer that is available in the board architecture or on your target machine that you want to enable for additional checks. Of course, you'll also need to build all the necessary modules. In this case, since we're interested in the Hancho Video for Linux 2 driver, I also enabled it. And then you can bring up your board using the kernel and the root file system provided that you generated. And my personal recommendation is to configure the bootloader so that it can boot the kernel from TFTP and mount a root file system via NFS, because of I like to avoid relying on an SD card because of the potential where after long test sessions, these kind of targets will probably stay in a laboratory running 24/7 for months. So you want to avoid using non-volatile media that is not too robust. Finally, we have to change some options of the configuration file we wrote before to suit it to our test target, which is the Rock-Pi4 board. Specifically note that the type option is isolated, which means that it's going to run in a dedicated board elsewhere, not in a virtual machine or anything like that. And in the VM section, which is still called VM, our target now is the IP of the board in our setup. Okay, so now that we know how Syzkaller works in general terms, we're going to see how to target the fuzzing process and how to make it more specific to a concrete part of the kernel, which is in this case the Hancho driver. Because unless we enable only and specifically the system calls that we want to test in the configuration file that we saw before, Syzkaller will try to generate programs using every system call that it knows about. That means every system call that is described in Syslang. And this is not what we want, because we don't want to fuzz the kernel in general in our board. We want to spend most of the time fuzzing one particular part of the kernel, our driver. So the first thing we'll need to do is to make sure that Syzkaller knows about the interface for our driver. And that means refining and improving the description of system calls. Now, the collection of system calls descriptions in Syzkaller is something that is a work in progress and it's always evolving. So this means that there will be some parts of the system call API which are described in more detail than others in Syzkaller. For example, the descriptions for Video for Linux 2 drivers were created a long time ago, and they are not complete. Furthermore, Video for Linux 2 drivers have a notoriously complex and big user interface, and it's always constantly changing, so the descriptions may be out of date, and if we use a recent driver, it will most likely use newer operations and flags that aren't maybe described yet. So the first step would be to make sure that our driver interface is properly supported in Syzkaller. That means including the necessary new syscalls and flags described in Syslang, so that Syzkaller knows about them and can generate code that use them. In the slide, there's a fragment, or a very simple example of how you can define new system calls, in this case for Hunter. As you can see, there are some things that are different from the normal OpenNAT descriptions. In this case, there are some parameters that are fixed, and there's a specific device file name, which makes the test process use that path name directly instead of trying to use whatever randomly generated file name. Now let's talk about device access. Most driver interactions in Linux involve opening a device file and working on the descriptor returned by open. The problem with this approach when it comes to testing is that a certain device won't always be accessible through the same device file name. This is something that will probably vary between setups. Syzkaller doesn't have any knowledge about the devices in your machine, so it makes a best effort approach by describing system calls using pattern matching to generate file name strings. So for Video for Linux 2 drivers, for example, you may find something like that long line in the slide, which, as you can see, tries to open /dev/video hash, and that hash stands for any number. So that system call, which is actually a pseudo system call, we'll talk about that later, will try to generate open system calls to any kind of file name that starts with /dev/video and then a number. So maybe it will start targeting device file names that aren't really in your system. So again, a lot of time will be spent doing nothing, trying to open something that don't exist, and it would be much faster if we could restrict the open system call to our particular driver. So a way to do this is to use some udev rules, so that udev will create a known file name for the driver that we want. So this way we can always be sure that we can reach our driver through the same device file name. And we can add these in the box in the slide, something along these lines, to the create image script that we saw before in the tools folder to automate the process during image creation. There's one more thing that we can do to make the fuzzing process more specific to our driver, and this has to do with pseudo-syscalls. Now, please take into consideration that pseudo-syscalls, well, incorporating new pseudo-syscalls to Syzkaller is discouraged because it makes the core of syscall bigger, and while it could make sense for pseudo-syscalls that are general and that can be useful for many uses. In this case, which is something that's very specific for one driver, it's totally discouraged. But still, I think it's good to I think it's good to show how they work and how they can be used. So, as we saw in the previous slide, system call descriptions in Syslang don't need to be exclusively system calls, but they also can be pseudo-syscalls. Pseudo-syscall is simply a function, a block of code implemented internally in Syzkaller. So when the code generation process picks up one system call and decides to use it for a test program, it simply outputs that call. It's just an instruction, and whatever instructions are needed to generate the input data, and that's it. But when it decides to use a pseudo-syscall, what it does is to take the whole block of code and output it in the test program using whatever parameters are needed in any case. So there are some applications of this which are quite important for fuzzing drivers. The first one is that this is a way of generating a static chunk of code that won't be reordered and won't change, like a known sequence of instructions that will always run in the same way. And this can be useful for preparing a setup for a part of the test, or to run an operation that it's made of many system calls that need to be called in a particular sequence. And it's also useful to generate input data in a controlled way, or even more useful in a programmatic way. Beautiful Linux 2 drivers are a good target for these kind of things, because most of the operations in these drivers involve calling a big long number of system calls in a proper order of execution, and some of them depend on the format and the contents of the input data. So leaving all of that to a random process will make it very hard for the fuzzing process to converge to a valid input that will reach the inner parts of the driver code. So now that we have Syzkaller running, after some time, if everything went right, we should start seeing the test corpus growing in the web GUI. And also we can see that the code of our driver is getting covered. And in case any bug happened, we should see a crash report, hopefully with a reproducer for the bug. A reproducer for a bug is simply a C program that triggers the bug when it runs. Now, Syzkaller will always try to obtain a reproducer every time it finds a crash. Although sometimes maybe it won't be able to do that because the bug may have been triggered because of a race condition, so it's not caused by the code that ran itself, by a test program, but maybe it was triggered by a certain runtime condition. So it's hard to reproduce simply by running a program, and Syzkaller can't be sure of that. Or maybe because there's more than one candidate that could have triggered the bug, because sometimes Syzkaller will run many test programs concurrently. So it's the interaction between these programs that may have caused the bug itself. Still, even if it can give you a specific reproducer for that bug with certainty, it will at least try to give you a high-level description of the program that caused the bug. An example of that is shown in the upper side of the slide. And also Syzkaller provides a few tools that can be used to turn these high-level descriptions into standalone C programs, as you see in the bottom part of the slide. So with a little manual effort, you can take one of these high-level descriptions and turn them into C programs and try to run them in the target and start investigating from there. The advantage of having reproducers is that they reduce the amount of time that we spent investigating a bug tremendously, especially if you take into account that Syzkaller already tries to minimize the reproducer to avoid having a lot of noise during the investigation. Finally, I'd like to mention Sysbot, which is arguably more widely known than Syzkaller itself. Sysbot is a continuous fuzzer and reporting tool, which has a public dashboard where you can see it in the link in the slide. And it has proven to be an invaluable tool for discovering new kernel bugs. What it does is simply to run Syzkaller on a bunch of kernels in a number of different platforms and keep track of the crashes it finds and report them with all the information it can find about them to the appropriate developers, maintainers, and the appropriate mailing lists. And as we saw before, Syzkaller gives as much information as it can about a crash, including a reproducer, and Sysbot does that, of course, but it also gives bisection information. So it's not only automating the bug discovery process in many cases, but it's also automating part of the investigation about the bugs. That's all for today. I hope you found the talk interesting and that you learned about the importance of Syzkaller as a tool for kernel improvement. Any contributions to the project are well received. Dimitri is putting a lot of effort into it and is always welcoming new improvements and developments on Syzkaller. So thank you all for listening. Have a good day.